Hello everyone, the paper I'm going to present today is titled Using Cyclic Noise as a Source Signal for Neural Source Filter-based Speech Waveform Model. So this is our latest work using Neural Source Filter Waveform Model for speech modeling. As introduction, the task of neural waveform model is to convert input acoustic features such as male spectrogram and F0 into the output waveform. There have been many existing models proposed. The first group of them is the pure machine learning based approach, including the famous WaveNet, WaveR, and another group combines the deep learning with signal processing techniques. One famous example is the LPCNet. The model we're going to present today belongs to the second group. It combines the deep learning with the signal processing approaches. Um, The model is called Neural Source Filter Waveform Model, or NSF for short. Similar to other waveform models, it uses 1D convolution to convert the input features into the generated waveform. However, one difference is that we also give a source signal, in this case a sine signal, as excitation to the signal. So this structure is inspired by the classic source filter architecture, but in this case, we are using the sine waveform as a source, while using the 1D convolution as a filter to convert the source signal into the output waveform. We have been using this architecture for many experiments, and it works quite well for female speakers. However, the question is whether the sine waveform is the best for all kinds of sounds we can alter. So if we check some speech samples, for example, the creaky sound, bracy sound, we can notice that the source signal for different types of sounds are quite different. Some of them can be quite random, but in other cases can be also sparse. So the question would be whether the source signal based on sine will be compatible with all kinds of sounds we can alter. So in this paper, we're going to find a better or more flexible source signal for the neural source filter waveform model. Let's go to the technique details. First, let me briefly explain the baseline model we use. So in this case, it's the NSM model with the harmonic plus noise structure. So the basic idea is the same as what I have explained in the previous slide, but there are some differences in the implementation. So as you can see in implementation, we use three modules to implement this network. The first module is the condition module to convert the input spectrum features or F0 into the upsampled F0 and spectrum features. And there is a source module to produce a sine waveform based on F0 and the neural filter module based on the harmonic plus structure. And there will also be a frequency domain distance for network training. There are so many details that I cannot explain in this short time, but if you're interested, please find the details in the reference paper. So for this presentation and this paper, we're focusing on the source module. So it looks like this. Given the upsample F0, we use simple sine generator to produce multiple harmonics. After we add the noise, we use a full connecting layer to merge them into one-dimensional signal. Uh, on the right-hand side, you can see one example of the generated sine waveform given the F0. So for the unvoiced part, it's random noise. For the voiced part, we generate a sine waveform. The fundamental frequency of which will be consistent with the input F0. So this is a general idea of how we produce a sine waveform given the upsampled F0. Of course, as you can see from this figure, the sine waveform is good because it's periodic in the voiced region, and this is highly correlated with the speech waveform, which is also periodic. However, sine waveform has less randomness in the voice segment. We cannot control the shape of the sine waveform. Um, the question is whether we can combine the noise with a sine waveform so that we can keep both the periodicity in the source signal, but we can also introduce more randomness or more degrees of flexibility for the source signal. So this is the idea behind the cyclic noise-based source signal for the proposed method. If we look at the details of the proposed source module, it looks like this. Again, similar to the sine-based source signal, we produce one signal for the voice segment, but we need to use additive noise or Gaussian noise for the unvoiced part. The equation looks quite complicated, but the basic idea is just to convolute the decayed noise with the pulse string. So let me briefly explain how it works with examples. So the first step is to produce a Gaussian noise, as you can see from this picture. So after that, we apply a exponential decaying function to change the amplitude of the Gaussian noise in the time domain. So the output noise would look like this, the blue signal. So you can see how the amplitude of this signal is decreased along the time. Meanwhile, we also we need to generate a pulse train giving the input f0. As you can see from this picture, the pulse train has fundamental frequency of 100 hertz. So giving this decayed noise and the pulse train, we produce output signal by convolution. So this is the conventional convolution in signal processing field, which is convoluted. So this is equivalent to just overlap and add the exponential decaying noises around the each spike of the pulse train. So it look like this, and the output signal would be the blue one, as you can see. Um, so from this picture, we can realize some characteristics of this cyclic noise signal. So in the long term, it's periodic. However, in the short term, it's random because we're using noise in each period. Okay, given this picture, we can explain more about the equations we use. So this is the equation based on which we generate a cyclic noise. It's a convolution of the decayed noise and the pulse train. The parameter beta basically controls the shape of the noise in each period. We set a parameter so that no matter what fundamental frequency is, the noise is always decayed by a fixed amount when it reaches next period. So the amount of decaying is determined by the beta parameter. So to give you more examples, so in this case, we're choosing the beta parameter equal to 0.43. So in this case, the noise decayed by zero point 0.1. So by changing this beta parameter, we're hoping that we can change the behavior of the source signal. So of course, the next question is to ask how can we set the beta parameter? The first way is to set beta parameter as hyperparameter. So we fix the value of the beta before we train the network. The second way is, of course, to predict the value of the beta from the input features. No matter what kind of network we use to predict the beta value, the whole network is differentiable. So we can train the network together and we can optimize the beta parameter. Let's come to experiments. For the experiments, we're using the CMU Arctic with the data of the four speakers, two females, two males. The input features include the male spectrogram and F0. We're trying the network in a speaker-independent way without using speaker vectors. Here are the results pulled over all the four speakers. So this is the mean opinion score for the quality. On the left-hand side, you can see the natural and WaveNet as a reference. In the middle, it's baseline and it's a model using either the sine-based excitation, the pulse train, or random noise. On the right-hand side is a group of the proposed method with a cyclic noise-based excitation. So the architecture of the NSM model is the same as the baseline. The difference is only the excitation part. For the first three cases, we're using the beta parameter as hyperparameters. So different value of the beta to control the different shape of the source signal. The loss system uses the trainable beta parameter, so we don't directly control or fix the value of the beta. From results, we can see for the proposed method, um, the difference is not significantly different, no matter how we choose the value of the beta. However, we can see the baseline, there is difference. For example, the sign is preferred over the pulse train and the random noise. Of course, this is a result over all the speakers. Once we decompose the results and check the results of each speaker, we can know interesting difference. So here's the results. Um, there are many messages we can raise from this figure, but the first thing we can notice is on the baseline model by comparing the sine, pulse, and random noise as excitation. One interesting find is how the male speakers prefer the random noise-based excitation, while the female speakers prefer the sine-based one. So let me play some samples from the natural to the generated speech.
He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming.
Female speakers.
He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming.
You may probably notice that the last sample of the female speaker sounds unstable in terms of fundamental frequency or perceived pitch. I think yes, that's the case because the female speakers have a higher fundamental frequency. I guess it would be more difficult for the network to recover the speech waveform with stable pitch from the random noise. Next, we can check the proposed method. Again, we can find a similar trend. So remember, for the three proposed method with different hyperparameters of the beta, the left-hand side one, the excitation looks more like the pulse train, while the right-hand side one looks more noisy. We can see similar trend for the female speaker. For the female speakers, the less noisy excitation looks better, while for the male speakers, they prefer more noisy excitation. Again, let's play some samples.
He was manifestly distressed by my coming. 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 He was manifestly distressed by my coming.
He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming. He was manifestly distressed by my coming.
So the losses system, I didn't show the detailed results here in terms of beta parameter, but the beta parameter looks really closer to the beta parameter of the beta 2, which is the value of 0.343. So yes, please check the papers for details. Okay, I have explained the results. Let's quickly draw a summary. So for this paper, we proposed the cyclic noise-based source excitation to replace the conventional source based on sine waveform for the neural source filter waveform model. And then we define the beta parameter to control the randomness in the source signal. Through experiments, we found that the cyclic noise is preferred or is more flexible than the sine waveform, and the good value of the beta parameter seems to be gender dependent. And there are more details about the results and also additional proposed methods in the paper. Finally, there are more samples on our website, including those on CMU and VCTK. We also open source the code based on PyTorch and including a tutorial based on Jupyter Notebook. If you're interested, please find these materials on the website. Thank you.